We are now in my Ubuntu test machine. It is currently empty and there's no running blockchain node here. But let us try to run a blockchain node now. Let us run a Moonbeam blockchain node. And once that is running, it should be listening at port 9944 at localhost. This would be what you call as the RPC URL that you configure in MetaMask for the MetaMask wallet to connect into this blockchain. Let us open the Chrome browser, and I already configured MetaMask to connect to my local blockchain, and we can review that configuration here. So I told MetaMask to connect to 9933, which is the blockchain node running here as a container local host, and then that particular blockchain is has a fixed chain ID which should be 1281. It is baked into the Docker image, and we have to use this value. And this currency token, you can name it any symbol, but let's just take the default symbol of the Moonbeam token, which is the glimmer. And then this is optional, but this is the block explorer. So that is how MetaMask is configured and our wallet is connected into it. Okay, we can see that we have three accounts: Cont, Docart, and Marks, and all of them have zero Glimmer tokens. Now let us try to do some testing here. I will copy the address of Kant, and let us go to the blockchain explorer. Let us go to a web interface that has that can show us a web page administration console of our local blockchain. And the way that to do that is to open this polka.js org and configure this development local node to point to 9944 and do a switch. I have already done that, and so we are now connected to my local blockchain. For example, by default, you can connect to other blockchains, like you can connect to Akala, and you have to do the switch. And in a few seconds now, we are connected to Akala. So right now, we are connected to the Akala blockchain. But let's go back and connect to our local host blockchain, which is a test development one. Let's go back here, click this, and do a switch. And now we are connected back to our Dockerized local only blockchain. This is a development blockchain, so it has provided us some test accounts with usable uh, amount of tokens. So since I have copied the address of Kant, I will give Kant some Glimmer token. I will give him like 9 Glimmer, and the unit is Melli. And I will click make transfer. So take note that Elite is the sender here, and our account in MetaMask, which is Kant, is the receiver. And in this particular type of transaction, the the blockchain, the scan explorer itself is acting like a wallet at the same time, because Elite's private key is is inside the Scan Explorer. Submit, and if we go back to MetaMask and check our balance, we have 9 Glimmer. Now that Kant has 9 Glimmer, let us give some Glimmer tokens to the cart. I'll copy the cart's address and I will send the cart with like send, paste the cart's address here and gave him like 0.69. Take note that in this second activity of transferring, we are using the MetaMask and the private key of Kant is in the MetaMask. Compare this to the first one wherein the private key is inside the Explorer itself. So the Explorer is also acting as a wallet at the same time. Right now in MetaMask is actually the real wallet. Confirm and sent. Kant has been deducted and then the card has now received the 0.69 token. We can also see here that Elite has a transaction count of 1 because Elite gave just sent a value of 9 Glimmer token to us to count when we did it here. Okay. Now we have now a functioning blockchain with a working Explorer. So let's go to Python code and launch VS Code. But before that, what I'm going to do here, let me describe it, is we are going to deploy this smart contract here, the incrementer. This smart contract is very small, just having 2 methods, increment and reset, which increments the number. We can retrieve it back because this is a public member field. We can increment it with any value and then we can reset it to 0. So this is the smart contract that we are going to deploy into the blockchain. The code that can do that is this one, deploy.py. Now you can ignore this one here because we are using this development endpoint here. So this is a dictionary and the key is development, which is referring to this one. So we are using this development key, which means we are actually targeting this local blockchain here. And we are establishing a connection, a Web3 connection to our local blockchain via port 9933. And we are holding that connection in this object. And in order to deploy the smart contract, it needs a sender to have some amount of token to pay for this initial deployment of the smart contract because there's payment by just deploying a smart contract requires some fees because when a smart contract is deployed, it will be part of the blockchain and it will execute some commands like the constructor of the smart contract. And if we go back here, the constructor of the smart contract when it's deployed will be invoked and that constructor will set the initial value of the state of the object. And since this is a state, anything that changes the state requires a gas fee. go back here. Well, this is the private key of of Alice. Take note. Uh, 5F 5FD9. And if we check here, who is that? Okay, let us check who is this 5FB9. Maybe it's okay. Hmm. Sorry. I was looking at the private key. So this is the address F24FF. Yep, Elite F24FF. Sorry about that. So Elite is identified by this address, and this is Elite's private key. So the flow here is that the we construct an incrementer uh, stub object of the smart contract, and okay, let us try to run this in VS Code there and put a breakpoint here. So let me go and start running the deploy.py code now. Okay, so it went into this breakpoint. Let me stop this and let me try to understand why that is. This was the from compile import ABI bytecode. Let me check. Okay, so we can see that there is a prom compile here which needed this compile.py. I have a previous discussion of the compile.py in my other session, wherein I explained that this is the code that compiles the incrementer, the sole smart contract into JSON, wherein the first component of that is the application binary interface, and the second will be the bytecode, and it is that bytecode that gets deployed over to the blockchain. And so this is the ABI, and this is the bytecode, and this is what is referred to by this header here, ABI and bytecode. So let me run again, and that is why we went through here. There. So now we have the ABI. We can hover the mouse and we can hover the bytecode. Okay. In my other video, I have shown the same value of the bytecodes printed in the console. Okay. So now that the smart contract has been compiled and we got the ABI and its bytecode now prepared, the Web3 subsystem of the Python is now going to establish a connection to our local blockchain identified by this IP address and port. Like we can look into the running chain now, and as soon as I press F10, you can see you can see a log will scroll here, indicating that somebody has connected into it. Let me press F10 now. Okay, no logs, maybe later. Then we initialize the dictionary, and this is the part where we provide the AVI and the bytecode into the parameter of this um, method contract creation object. This is still at the phase where the client code is trying to prepare the smart contract. So there is no data transfer that is happening here, just preparing the smart contract. Then this part here, the incrementer constructor, we specify a 5, which means the constructor will receive an initial amount of 5. So the initial value of the member field would be 5. And then we build this transaction, and then we specify who the contract creator is, which is the from, which is this one, the address. And then we always we specify the nonce of the sender address. Here first we retrieve the nonce from the blockchain, and we supplied it into the nonce. The nonce is an integer that keeps on increasing every time an address has successfully transferred a value. Every time a sender has successfully sent a value, its nonce will increment by 1. But the receiver nonce will not increment. It is the sender's nonce that increments. Therefore, you can correctly conclude that the nonce is a count of how many transactions, how many send has happened from that address. So we construct now the transactions. No network transfer will occur here. We are just constructing the object, specifying the 5 in the default constructor of the smart contract. There. Okay, let's maximize this a little bit. And then this is the part where the sender has to sign the transaction. This is the unsigned transaction, which is provided here. And this is the private key of the sender. And it will give us a signed transaction here. There is no network transfer that occurs here. What happens here is just this transaction here is just signed there. And that will be what it looks like when it is signed, and this is how it looks like when it is unsigned. So tx is an unsigned transaction. I mean, construct txn is an unsigned transaction, and this one is a signed transaction. Now, how this one on the other hand, the send raw transaction, is the instruction that does a network transfer to the blockchain. It talks to the blockchain. Therefore, you can definitely see a log scrolling here as the blockchain is about to receive that particular transaction. And you will notice that what is provided is the signed transaction here, tx and the return is tx hash. Let me press F10 now. Before doing that, I will move the VS Code here so that we can see that the log is scrolling. I will press F10 now in 3, 2, 1, 0. So you notice that indeed the blockchain has received the transaction. Now, the hash that is returned here is not the transaction hash yet. We still have to wait for a transaction receipt. Well, the transaction receipt takes some time as when the transaction is submitted, it is still in a queue and about to be mined, and that takes time to happen. So this one, when we wait for transaction receipt, we're actually waiting for the transaction to be finalized and becomes part of the block and hence is immutable because it's now in the blockchain. I will press F10 now and there. If I we can see at the this is the transaction receipt and then the contract deployed at address. I will press F10 and this is the contract address 0.970951. Let me copy this. So the contract is now deployed into the blockchain. It is now in the blockchain, ready to be called, and the address of the smart contract is this one. Let me copy this address. So to invoke or to call a method in the smart contract, we need the address of the smart contract, which is this one, and the ABI or application binary interface of the smart contract. The ABI, as I explained in my other video, contains the list of callable methods of a smart contract. Without an ABI, you cannot call smart contract. So there are two things that you need to have in your possession in order to interact with a smart contract. You need to have the smart contract's address, this one, and the smart contract's ABI. Now let us open the increment pi. This is the code that will invoke the smart contracts increment uh, method. You see it is here. Okay, so it is here. So it looks the same. Take note that from the we need the ABI, but we no longer need the bytecode. The bytecode is now copied into the blockchain. It is now there in the cloud. What we need is the ABI. This is a JSON string that contains the list of functions that we can call in the smart contract. As usual, we connect to the blockchain using Web3 and we need a private key and an address. When we engage with a smart contract, we are engaging it from the point of view of a externally owned account or from a user, which means somebody is calling the smart contract and that somebody is identified by this address. And because that somebody guy that the caller needs to sign the transaction, then that guy, that caller also needs to 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 have ready its private key in order to do the transaction. And we can see here that the contract address is this one. So there is a formula on how to compute the smart contract's address. It can actually be known from the sender's address and some data there that to make a long story short, you can calculate the address of the contract even before you send it to the blockchain. So the blockchain is not the one who calculate the smart contract address. It can be calculated locally without even involving the remote blockchain. That's the point there. So we have an ABI of the smart contract, and then we have the address, and then this is the value that we're going to increment, and we instantiate an object of the smart contract here. We specify the contract address and the ABI, and this object, the incrementer, we invoke its increment method. Okay, we invoke its increment method and we supply the value of 3. So we increment it by 3. Remember that at contract deployment, we supplied 5 to the constructor. So right now, the smart contract has an initial value of 5. So if we increment it by 3, then if we do, okay, there is no get call here. It will be in the next session, but let us just complete this flow here. Let me put a breakpoint here and start debugging. So let me go to the blockchain console so that we can see some logs crawling and we would be aware of the exact timing conditions of when things are happening. So we are connected now to the blockchain using Web3 via this URL, initializing the private and public key, initializing the destination contract that we are about to call the contract address, the value of 3, we are going to increment with the value of 3. We are now creating locally the contract object to prepare to invoke a call. We are instantiating the contract object there. Although we have a contract object here, calling the increment method does not really execute code in our local machine. The code, remember, if you remember, is residing remotely in the blockchain in the cloud. We only have some sort of a stub of the functions of the contract locally. But when we call one of its functions, such as the increment, the execution of increment actually occurs remotely in the blockchain, not from our local machine here. Okay, so that's the principle. So we build now the increment. We are now attempting to call the increment when we build the increment transaction by supplying who is doing who. The one who is sending the increment function is the from address, and of course, as usual, we need to get the nonce. Okay, now as usual, we sign. Whoever is doing the transaction has to sign it. So the signer has to provide his private key. Now this is now the signed transaction. We are now about to send this signed transaction to the network. Send raw transaction. You can see now that this log here will scroll in 3, 2, 1, 0. You can see the timing is perfect. As soon as we invoke the send raw transaction, the blockchain receives it, but it will take a while for the transaction to be mined. It's not immediately mined because there's a lot of uh, things going on before a transaction is mined. There has to be consensus or whatever. The gist is that it's not instantaneous. So after a few seconds, we will have a transaction receipt there, and then we say that trans transaction successful with hash of this one. So in summary, we deploy the smart contract and then we invoke the increment. when we deploy the smart contract, we set 5 as its initial value, and when we call the increment, we provided 3. So therefore, right now, the smart contract there in the cloud has a value of 8. So let's go to the next transaction, which would be the get. Yep. So the get. Mhm. So the get operation is to read the value of the state of the smart contract. This operation does do not change the state of the blockchain because it is a read operation. If you recall now in the smart contract here, the number field is declared as public, and as such, it can be read publicly. But take note, reading this field is a read-only operation. It does not change anything. Okay. Therefore, any operation that does not change the state of the smart contract has no gas fee. So that is why the only thing that we need here is the contract address as usual, because we need to invoke a smart contract, and that's it. There's not even a need to specify uh, who is doing the operation. So let me put a breakpoint here and run this. There. As usual, we always connect to the blockchain using the Web3 endpoint. And then this is the address of the smart contract. And then we instantiate a stub object of the smart contract incrementer. And then we invoke we retrieve the number to retrieve the value of number of the smart contract right now in the blockchain, which we know is should be 8. So we should be able to see in the variables here. Okay, let me in the locals. Yep, you can see here the number is 8 correctly, but it is also printed here, and the current stored is 8, which is correct. When we deploy the smart contract, it was initialized with 5 in the constructor. We we did an increment of 3, and then now we did again a get, so it should be 8. So that means if we do another increment here, so it's of maybe 12, let's change this to 12. So let's increment it by 12. It is right now it is 8. We increment it by 12. Let's do that. Let's run again this program. So we already know what these lines are doing. But what I always like is to timing the scrolling lags in the blockchain as soon as I do send row transactions in 3, 2, 1, 0. So it feels nice to have to have this connection that the client is now talking to the blockchain, and we now incremented what was previously 8. We incremented it with 12, so it should be 20 now, and at the cost of a gas fee, because we changed the state of the smart contract. We also changed the state of the blockchain, and such kinds of activities requires gas fee. This account is doing the payment of that transaction. Okay, there. So it's 20 now. If we go back to get again, let's run the get. It should be 20, and there we have 20. But because again, this is a get operation, does not change any state. Yep, it it transmitted a value into the network and it establishes a connection to the blockchain, but it didn't change the state of the blockchain. Therefore, no gas fee is needed. You can call a method in a smart contract, and if that method does not change the state, then there's no gas fee needed. There's no even need to specify who is the sender, the from, no public key, no address. Okay, so so that's all for now, and I hope this explanation has shed some light and demystified what a smart contract is.